Hello, good afternoon, and welcome to this Conservation Applied Research and Development webinar. I am Mary Sue Lovenstein, the R&D Program Administrator at the Minnesota Department of Commerce, Division of Energy Resources. With me today is Mark Garofano, who is an energy engineer at the division, and where he performs engineering reviews of custom efficiency projects and also leads the department's efforts to maintain and update the technical reference manual that utilities use to calculate the savings and cost effectiveness of their conservation improvement programs. Mark is also the project manager on the research that is the subject of the webinar today. And our presenter today is Josh Quinnell, who is a senior research engineer at the Center for Energy and Environment. Josh has 12 years research experience in solar energy, heat and mass transfer, and energy efficiency. Currently, Josh is working on building energy efficiency projects, grid modernization efforts, solar energy deployment optimization, energy storage, and strategic electrification. Josh's recent work includes HVAC duct leakage and retrofit sealing, condensing boiler efficiency, energy recovery ventilation, and garage containment transport, as well as residential furnace efficiency retrofits. Before we start, I'd like to go over a few webinar basics. All attendees will be in listen-only mode, and as questions occur to you during the presentation, please type them into the question box in the GoToWebinar panel and send them to us. We will address all questions at the end of the presentation, but if for some reason we don't get to all questions, we will answer them later and email all participants a copy of the Q&A from the webinar. This webinar is being recorded and will be available on both CEE's and the department's websites at a later date. And finally, the slide deck for this webinar is available as a handout on your GoToWebinar panel, where you can download it at any time during the presentation. This webinar is one in an ongoing series designed to summarize the results from research projects that are funded through Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. Its purpose is to help Minnesota utilities achieve their 1.5% energy savings goal. A utility may reach this goal either directly through its conservation improvement program or indirectly through energy codes, appliance standards, behavior, and other market transformation programs. About $2.6 million of this fund is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. As you can see by the pie chart here, projects funded to date have been in all building sectors. The subject of today's webinar is the residential sector and reports on the results of a field study to determine the increased efficiency resulting from the installation of an innovative moisture and heat transfer retrofit device on residential furnaces. Now I'm going to turn it over to Josh.
All right, thank you so much, Mary Sue, for that introduction. I'm really excited to be here today to talk about this project with you guys. It's a project I've been working on with CARD funding now for 3 years. We've had a lot of challenges in this project. We've overcome most of them, and it's just a really exciting technology that I get to talk to you about today. Before I launch into it, though, I want to make 2 important acknowledgments, and they are to our project partners that we worked with on this project. First, we work very closely with the Gas Technology Institute, or GTI. They're actually the developers of this technology, and they not only designed and built these prototype units for us, but they were an instrumental technical resource throughout the whole project. I also want to acknowledge CenterPoint Energy, Home Service Plus, who are our contractors on this project. And they not only were super excited to participate, but they did a phenomenal job. And I think a lot of the results I'm going to show you are a testament to the good job they did on this project. So my talk today follows a pretty normal outline. I'm going to go through more or less an abbreviated version of the final report that will be posted after this talk. I'm going to give you a little bit of background on the technology that we're working on, justify why I think it's a worthy research pursuit, and then outline some of the objectives we have for the work that we have completed. I'll quickly go over our methodology and share with you what I think are some of the most important choices we made when designing and executing the study. And then I'll spend most of my time today discussing the results and what we think they mean for the TMH technology and its future. And lastly, I'll wrap up and kind of share with you where we're at now and where I hope we can go. So a quick background. Today, space heating in single-family homes is mainly done with natural gas-powered forced air furnaces. And we basically have two types of furnaces on the market. We have standard efficiency furnaces. They've been around for about 30 years. They typically have an 80% efficiency, so they convert about 80% of the incoming natural gas after combustion into heating building air. They typically exhaust high-temperature flue gases out a standard exhaust that exits the top of the single-family home. About 15 years ago, we started installing high-efficiency furnaces. Their unique distinction is that they have a secondary heat exchanger where they extract even more energy out of this combustion process. And they do so by cooling the flue gases to a very low temperature and letting some of the water condense out. This additional energy allows them to reach efficiencies that exceed 90%, or on average they have about 15% less gas usage to meet the same heating load. So today, high-efficiency furnaces command most of the market, but we still sell standard efficiency furnaces. But most of the systems out there remain standard efficiency. And that's really the potential, the savings potential I want to talk about today. So natural gas savings in single-family residential heating is the largest savings opportunity that exists in the state of Minnesota. 1/3 of our natural gas consumption is in the residential sector. 2/3 of that energy, or of that natural gas, is used for space heating, which gives a net of about 20% of natural gas in Minnesota used in our forced air furnaces. So any efficiency measures we can apply or improvements we can make will have a massive impact statewide if we can target this end use. And today, the only real way to save energy, assuming our heating loads are constant, is to make this upgrade from a standard efficiency, nominally 80% efficiency furnace to a condensing furnace with 90+% efficiency. And this poses a lot of problems. Namely, we're still installing a lot of standard efficiency furnaces on the market. They still command about 30% of the statewide market, which means nominally we're installing 15,000 to 20,000 of them per year. This is sort of an advantage, but these devices, these standard efficiency furnaces, are also incredibly long-lived. They're very robust appliances, and they essentially achieve their nameplate performance until the day they fail, which in many cases is 20 or 30 years or longer. So what this means is if we want to think about capturing these savings from high-efficiency home heating, we either have to wait for these robust appliances to fail, or we have to replace a perfectly working appliance, which is a suboptimal decision. And so today I'm going to try to make the case that we need an alternative for getting these savings that come with high-efficiency heating. And what we really need is a retrofit. I want to make the case that there's a massive opportunity to retrofit existing standard efficiency furnaces to try to claim some of these savings. So first I'll tell you what's on this plot before I share with you how we got it. But this is essentially the number of standard efficiency furnaces that are installed in the state of Minnesota as a function of time. And so this takes us through the year 2060. And we came up with a simple model that allows us to forecast the number of standard efficiency furnaces as a function of many variables that will impact how long they last. This includes average furnace life, their current replacement rate, i.e. the market share of condensing furnaces, the rate at which that changes over time, as well as any future policies that may mandate 90% plus efficiency furnaces. And to make a long story short, if we run a bunch of scenarios with all sorts of combinations of these parameters, we get all of what you see in the blue area here, kind of outlined by the longest lived standard efficiency population and the shortest lived population. The main point here is there are hundreds of thousands of standard efficiency furnaces that under most scenarios are going to be here for decades. And this is a real shame because to get those heating savings by moving to high efficiency heating, we either have to replace these units prematurely or we need a retrofit. What we studied in this project is a retrofit opportunity. It's a device called the Transport Membrane Humidifier. This is actually a technology developed by the Gas Technology Institute as a whole house humidifier replacement. It's essentially a secondary heat exchanger that we're going to add onto a standard efficiency furnace that's going to make it perform a lot like a condensing furnace that has two heat exchangers. The heat exchanger in the TMH case, though, has some special properties. Instead of a stainless steel, it's actually made out of ceramic membrane tubes, and this gives them the ability to transport water from the flue gases into the building air, which provides a humidification effect in addition to heating. These ceramic tubes are engineered on the nanoscale level to give a sequence of pore sizes that allow the transport of water across the membrane but prohibit the transfer of combustion products. so we don't transfer CO or any other undesirables into the building space. And so what we get is a device that can extract additional energy out of the flue gases, so improve the efficiency while giving some humidification benefits. I've got a picture here of one of our prototype units. On the picture on the left, we can see these ceramic tubes from the outside. This is the building air travels along the outside of these tubes. On the right, I have a picture looking into the tubes through one of the manifolds. This is where the flue gases travel. So the flue gases pass on the inside of the tubes, and they transfer heat and moisture through the tube walls into the building air. I've got an animation to kind of walk you through how this works in relation to a regular furnace. So to go through a regular furnace first, we have all these components, but mainly what's important is we pull building air into our furnace system through our blower. It passes over the heat exchanger where it gets heated up from the flue products that are from the combustion process. The flue gases then transfer out at high temperature out of the building. If we put a TMH in the return duct, we preheat and prehumidify that building air before it enters our furnace. And then after the heat is transferred in the main heat exchanger, we pass the flue gases through the TMH and further extract some energy. So if we zoom in on the TMH unit itself, we're taking those flue gases that would otherwise be discarded, we pass them through the TMH unit, and then we extract heat and humidity before letting them exit the building in a new sealed PVC exhaust that carries the low temperature flue gases. So I've mentioned a couple times that the TMH works like a humidifier, so let's take a moment here and talk about humidification. We've got a basic physics problem in cold climates, and that is cold air does not hold moisture. This causes our homes and all of our buildings really to dry out in the wintertime. We can see that in this plot I'm showing here of outside absolute humidity as a function of month per year, and this is compared against the red band, which is our ideal indoor humidity levels. We can see that in the heating season, say October through April, we consistently have humidity levels that are less than what we want in our buildings. So any exchange we do with the environment, whether it's mechanical ventilation or natural ventilation, dries out our buildings. In a lot of cases, these humidity levels are 5 or 10 times lower than what we like in buildings. And we all know, as recent weather has been a reminder, what it means to have dry buildings. There's a lot of negative consequences associated with extreme dryness. First of all, we have general discomfort. Dry air feels chillier and draftier due to a lower apparent temperature. We're all familiar with the respiratory and skin irritation problems that come with dry weather. Cracked skin, cracked lips, coughing. We have annoying issues with static discharge. We have issues with our beautiful wood floors cracking up and creaking due to the contracted wind. Frankly, what we have is sick building syndrome. We have acute health and discomfort issues associated with the typical conditions in our buildings. And I don't know what to say other than that we're hardy, and most of us just deal with this year in, year out, year after year. Humidification in buildings in residential buildings is usually quite rare. That said, humidification is one option to overcome these challenges, but it sort of brings its own problems. Humidification, if done to ideal comfort levels, requires a significant amount of energy to evaporate the water. This could be, in some cases, up to 20% of the regular heating load. And then humidifiers, in terms of the specific equipment, as well as the excess humidity they may bring into a dwelling, are associated with their own problems, including mineral deposition. This is white dust, microbial growth in the humidifiers themselves and or in places with high humidity, and their own health issues. So we've got this issue here. We have a device that can give performance advantages and it can give some humidification benefits, but humidification is sort of a double-edged sword. And these are really the objectives we're focusing on in this study. We want to make sure that, first and foremost, the TMH lives up to its performance potential, and it is, and we want to determine if it is a viable alternative to high-efficiency heating, specifically a retrofit alternative. Then we want to also measure the humidification benefits of the TMH. How does it compare to other technologies as a whole house humidifier? On the flip side, we need to be extremely aware of the consequences of adding humidity to houses in the wintertime. We need to understand this humidification benefit and also measure and make sure that there are no adverse consequences of excess humidification, but if there are, to document them and understand where and how the TMH should be installed. So to do this, we essentially engaged in a field study that was predicated on designing and installing prototype TMH units and measuring them in the real world. I will briefly outline our methodology here. We have a lot more detail in our final report, but we did spend a fair amount of time on site selection variables that we anticipate will influence TMH outcomes. The purpose of this is because we only have a few sites that we can test the technology on, but we want the results to be as broadly applicable as possible when considering potential TMH installations on Minnesota's single-family homes. We then worked with GTI. Well, actually, GTI worked at our behest to design these TMH units for our research sites. We contracted with CenterPoint Energy Home Service Plus to install the units in our research sites. Meanwhile, we came up with an experimental plan so that we could measure their performance over a large variety of conditions. So we instrumented the units and set up a monitoring regime so that we would understand how they work. And this is all in support of analysis so that we can document the performance, the humidification benefits, the energy savings, as well as understand any adverse consequences of adding humidity. So I'd spend longer than normal in talking about site selection because in this project, it's really important that we understand indoor conditions and feel confident that we understand where and when the TMH will work. So the easy things out of the way, we want to make sure the TMH works in a variety of makes and models of furnaces. So we have 4 different manufacturers and 4 different models of furnaces. For other reasons, we picked furnaces in this project that are old, but they still have a pretty large range in lifetime from 16 to 27 years. The sizes on these furnaces don't vary much, but nominally most furnaces in Minnesota have a relatively narrow size range. And then again, they're all standard efficiency induced draft furnaces. Most of our effort in site selection was based on characterizing the indoor conditions in Minnesota homes so that we could pick representative conditions. And it turns out that there's not actually a lot of data on what indoor humidity conditions are like in Minnesota homes. So we picked some proxy variables that we assumed would represent indoor conditions, and they are occupant density and envelope leakage. These parameters are useful, first of all, because there's a lot of data on them, so we can make sure that the values we pick are representative of the homes in Minnesota, but also there's a physical basis by which they're related to indoor humidity. The first one is occupant density. This is sort of a proxy for the rate of humidity generation in a building. So people generate humidity, whether they're breathing or cooking or showering. All these things happen in proportion to the number of people. Secondly, we have envelope leakage. As a reminder earlier, we talked about how we have cold air outside in the wintertime, and so any air exchange with the environment tends to dry out our homes. So envelope leakage is a proxy for the rate of humidity removal, as it approximates how much exchange there is between whatever indoor conditions exist and the very dry outdoor conditions. I'll dwell on this a little bit longer. This is our envelope leakage versus occupant density selection criteria that we landed on in this study. There's a lot going on here, so I'm going to walk you through it. I'll direct your attention to this plot in the lower left corner. So this is the percentiles that we picked for this study in terms of air tightness and occupant density. And you can see that we're focused on the right half of the plot. In other words, we tried to find sites in this study that represented above average rates of humidity generation, and then nominally the 35th and 75th percentile of air tightness. And this gives us this kind of parameter space that we expect will tell us that TMHs will either work or not work in these above average humidity environments. And upon that, we can draw some conclusions about the remaining part of that plot. So in the real world, we don't deal with percentiles. We have to measure things. And that's what this large plot shows. Those percentiles translate into the gray dots and the gray regions on the larger part. And so those percentiles, for example, mean about 8 CFM50, 0.8 CFM50 per hour to 1.25 CFM50 per hour, and an occupant density of approximately 1.05 to 2. And our targets are there. You can also see where we landed in the study. We had data that we used to screen, and that was the blue dots, so a little bit outside of our target ranges. And then finally, when we recruited participants in the study, we have the red dots. So you can see we don't have our perfect parameter space that we intended, but we still do have generally the right area that we feel represents more or less 50 or 60% of the homes in Minnesota that would consider TMH technology, and we have a variety of conditions that we intend would imply different indoor humidity conditions. And I'll just say now that out of the 4 homes, we essentially have 2 homes we would qualify as dry to very dry, 1 home that's mildly dry, and then 1 high humidity home. So this strategy did allow us to capture a variety of indoor environments. So it was our responsibility to instrument all of these units so that we could take the measurements we want. This generally involved taking a lot of characterization measurements at the beginning and ending of the project. For example, furnace, airflow, house envelope tightness, supply and return duct pressures, blower power draws, etc. And then mainly we instrumented these units with temperature and humidity probes so that we could measure the sensible energy and the latent energy added by the furnace and the TMH, where the sensible energy is the temperature change across the components, and the latent energy is the humidity added by the TMH. We also added temperature, humidity, and wood moisture sensors throughout each of these homes so that we can understand how the indoor conditions responded to the TMH or regular furnace operation. From all this, we get energy output rates from our system in BTU per hour that tells us that we can relate to our heating loads and use to calculate savings, etc. We can calculate steady state efficiency, so we can compare the net efficiency of our furnace plus TMH system, and then again we directly see changes in the indoor environment as a consequence of running our TMH or running our regular furnace. I want to take a detour here to talk about code compliance and permitting. So it was our intent in this study to go through the regular permitting procedure to get the TMH installed. Lo and behold, building officials tend to be uncomfortable with researchers installing unlisted devices in people's houses. The bottom line is that we were able to get temporary permits for this study, but it resulted in a lot of negotiations and a lot of delays. And it's something in the future, we would start very early in the project. Ultimately, through these negotiations, though, we had to perform some additional requirements to get these permits. We had to test these devices in the lab for both performance and safety to make sure that they were meeting specifications. We had to develop installation instructions and an operating manual that had to be on site at each site. We had to put together a technical report stamped by a professional engineer that certified the design and safety of the device. And then we had to have one installation subject to Underwriters Laboratories field certification. And then we had to follow that procedure at the other sites. So after we got through all this, we had permission to install our units, and that's when we brought in CenterPoint Energy Home Service Plus as our contractor. Our goal was to stick with one contractor and one crew so that we could kind of document the installation process with as few variables as possible. And documenting the installation is really important. We have a rough idea of what the capital costs of a TMH are, but no real data on how long it takes or how much it will cost to install them. So by documenting this, you'll see in the results later, we were able to come up with some estimates. Because it's essential that these TMHs be installed fast and cheap. They essentially have to be significantly cheaper than a condensing furnace for it to be a viable alternative. So we were there. We had a hands-off approach after we delivered the instructions to the contractors, but we were there to observe and document all the installs so we could later extract the data and make estimates. So we worked with Home Service Plus to install these units, to understand the labor costs of installation, determine any of the barriers of installation, and then describe, if any, learning curve associated with the installation of these devices. And I'll say right now that CenterPoint Energy Home Service Plus pretty much impressed us at every step. They not only, the contractors we work with, they not only understood it right away, but they needed almost no help on our part to execute very efficient and fast installs. In fact, I'm going to run through that with you right now. There's 5 steps to install a TMH. These guys come on the site, they remove the old return drop, they remove the vent, and then they take some measurements to figure out the new return drop, how it will fit in there with a TMH. So the guys right now, they're just making a quick measurement. This site took about an hour of extra work because they had to make a transition to bump out the TMH from the wall. The next step, the TMH drops right in just like any other sort of ducting. Uses slip and drive connectors. Here they're putting it in, and he's just wrapping up the seams with foil tape to eliminate air leakage. The next step is to reinstall the B vent Usually this would go from the furnace to the TMH. You can see we have 2 vents installed in this study. So these 2 vents allow us to go between the TMH and then the regular furnace operation. This is how we enable the alternate mode testing and how we can, in real time, change between whether it's TMH operation or bypass operation. The next step is we need a new vent for our TMH exhaust. It's now low temperature, around 110 Fahrenheit, and it's saturated with water vapor. In order to prevent that from leaking out, it needs to be evacuated from the building in a sealed exhaust, in this case made of PVC, so we put in a condensate trap, we pipe that out into a new termination. The last step is to wire up the unit. In this case, we need to wire in the new inducer fan in parallel with the old fan, and we also add a safety switch for the study to make sure that if anything happens downstream of the TMH, the furnace will fail to prove. We also had to do some additional work for the study and install some switches so that we can switch operation between baseline or bypass mode and TMH mode. So that's it. We successfully installed 4 of these units. It took us a little bit longer than we wanted, but we were still able to operate them for a long period of time. We monitored these 4 systems for between 1 and 2 heating seasons. This enabled us to get alternate mode testing, in other words, TMH and bypass modes in each of the seasons. We were able in this study to reach design conditions. Got to -19 or -20 last year, which is very nice for me. In the last several years of cold climate research, we've had some trouble reaching design conditions. But this essentially let us get data on thousands of furnace cycles during both TMH and bypass mode during ostensibly the same conditions. And in the end, we get a tremendous amount of data on these units over a large range of operating conditions for 4 different furnaces that operate in 4 different ways in 4 different houses. So we have a phenomenal amount of data here, and we're really pleased that the results for all these different operating conditions were fairly similar and unambiguous. So I'm going to jump right into it. This chart is the headline chart from our study. We have our net output in terms of BTUs per hour, plotted it for each of these sites in bypass mode and TMH mode. So by the way, these are steady state performance results, so typically after 5 or 7 minutes of operation. So our bypass efficiencies are the easiest number to look at. They are between 76 and 82%. This is nominally what you would expect from an 80% furnace, so everything looks okay there. You could see that when we operate in TMH mode, we get universally higher outputs. These are about 18% higher on average, higher outputs than in bypass mode. We have nominally 91 to 95% steady state airside efficiency. These are competitive with premium condensing furnace efficiencies. If we dial into that a little bit further, we can see where this energy comes from. So again, I'm looking at total system output here in BTU per hour. I also have it given for each of the components for each site. So again, these furnaces are 80% efficient. So the green shows us that most of this energy, about 80%, is coming out of the furnace heat exchanger itself by increasing the temperature of the building air. Then on top of that, in TMH mode, the TMH is adding 2 other types of energy. So we get another temperature rise out of the TMH from about 2,700 to 7,800 BTU per hour. That's approximately a 5 or 7 degree temperature rise we get from the TMH. And then we have the TMH latent energy, which adds the humidity to the building air. And this is nominally the same, about 2,400 to 6,900 BTU per hour. We add this all together and we get these efficiencies that are in the mid-90s percentile. So in summary, if we average these heights, we're getting 9% natural gas savings for space heating. To meet the same building load, a TMH will use, a standard efficiency furnace equipped with a TMH will use about 9% less natural gas because it's taking 5,300 BTU per hour out of the flue gas. This results in about a 5 to 7 degree temperature rise across the TMH, and you see about a 5 to 7 degree temperature out of the supply, higher temperature out of the supply. The humidification savings are a little bit more nuanced. We do get another 9% natural gas savings if we're displacing other humidification systems. The TMH is giving its humidification effect from the flue gas at about 5,200 BTU per hour, whereas other humidifiers would have to take this from the building air, and that would have to be made up by additional space heating. However, if we still are operating humidifiers in our house, it's still possible to use additional energy for humidification, so we have to be careful. It may not be displacing all the energy from humidification if other systems are remaining operational. On the other hand, if our house is not operating humidifiers, it does not displace any previous humidification, and there are no savings. But it still remains a significant non-energy benefit that we are improving the humidity in these buildings. And that's a pretty good segue into the analysis of these devices as humidifiers. So we were able to operate 3 of them through enough cycles so that we could test their humidifier output over a range of conditions, and we show that on the box and whisker plot here. The median output for the 3 devices we installed were 10 to 21 pints per day. Whole house humidifiers tend to be rated in pints or gallons per day, so that's the reason for that unit. Each of these has a maximum humidity output ranging between 23 and 55 pints per day. This is more or less in the same range of most whole house humidifiers, which are typically rated at 48 to 65 or so pints per day. And then if we look at each of these plots, we do see that there is a large range of output for each site. And for all the sites, this is between about 8 and 28 pints per day would be the interquartile range that we see in this study. So you might look at these and say, well, we have a sort of a variable humidity output that might not be what we want. But in fact, if we look at the data in a different way, it's exactly what we want. What we get with TMH is a dynamic humidifier output that puts out more humidity when we need humidity. And generally, we need humidity in cold weather. Here I show humidifier output again as a function of outside air temperature bins. And we can see a pretty clear trend for all sites that they output high humidity in cold weather and almost no humidity in mild weather. And they do this naturally without any kind of control, in contrast to a whole house humidifier. And that's because the mechanisms that drive the TMH output allow this to naturally happen. So the TMH output is proportional to how much it runs, and furnaces run more in cold weather than warm weather. So as the TMH runs at a higher runtime in the winter, it will output more humidity. A secondary effect is that the TMH output depends on the humidity difference between the flue gas and the building return air. So as the humidity in the building return air increases, as it tends to do at higher outside air temperatures, the TMH, again, will output less humidity. So both of these things kind of combine to give us an explanation for why this TMH's humidity output is self-limiting, and in fact reassures us that some of these concerns we initially had about over-humidification or uncontrolled humidification are not going to be observed in practice. So what does the TMH do on the indoor conditions? I'm going to show you a couple plots and walk through them with you to explain how the TMH changes the indoor environment. Here is site H3. Without a TMH, it has essentially a heating season indoor relative humidity of about 32%. This is dry to very dry indoor environment. On the plot, I'm showing relative humidity at the thermostat as a function of outside air temperature in bypass mode and TMH mode. So although the average humidity in the house is 32% heating season, you can see that below freezing, it's quite dry. It's 20%, sometimes even below 20% would be the average humidity in this house at those outside air temperatures. And the 32% average is achieved only because there's significantly higher humidity during mild weather. If we flip on the TMH, though, we can see, especially at cold temperatures, there is a large increase in relative humidity. About 10% in this case. We have about a 10% increase in relative humidity when operating the TMH below freezing temperatures. And probably the second most notable feature of this chart is that as we get up to these higher temperatures, say above freezing, there is essentially no difference between the humidity during TMH operation or bypass operation. This is partially because the TMH is putting out a very small amount of moisture at those temperatures, but it's also because at those temperatures, the outside air can hold a lot more moisture, and that becomes a more important factor for determining indoor humidity rather than the small output of the TMH. So we have another site that was very much like this. I'm not going to show that to you. I'm going to jump forward to site H4 because this was a really unique site. This is what we would call a site, didn't have humidity problems, but it would be a high humidity home. And frankly, it's not the best candidate for a TMH installation. But it does make a great site to test a TMH if we're worried about what happens when we add humidity to a home that frankly has a high humidity level. So the humidity in this home in the wintertime averages about 50%. Again, it's a lot drier in the cold weather than the warm weather. But even in the coldest weather in bypass mode, we see indoor humidities of about 40% to 45%. In this case, the TMH is still adding moisture, but it's adding a lot less, or the effect on the indoor environment is a lot less. The indoor humidity is about 5% higher when we operate the TMH below freezing. And then again, as we get up to mild temperatures, the humidity in this house does increase, and it's about 60% in mild weather, which is probably about as high as we would like it in this home. But again, we can see that that is not really impacted by the TMH. In fact, we have slightly higher relative humidities in bypass mode than TMH mode. And then again, this is largely a function of what the outside air humidity is at those temperatures. We have a larger outside air humidity, and it's the air exchange with the environment that drives the indoor humidity compared to the low output of a TMH. So in summary, the TMH does exactly what we wanted it to, and this is a pleasant surprise. In dry conditions at low temperatures, we increase indoor humidity by 10%. So this is below freezing and below relative humidity about 30%. In dry houses, over-humidification is avoided in warm and mild weather because at these temperatures the TMH is outputting less, and then outdoor humidity is a more important factor for determining indoor humidity than the humidifier output. And then again, when we put this in a high humidity home, we see an overall reduced output, and we see a smaller impact on the relative humidity. So I know that none of this is what you came for, and really what we want to know is the energy and cost savings of the TMH. So the good news is that we get direct natural gas savings from operating this unit. So it's really easy to take our savings measurements and apply them to weather normalized loads. So we've done that with the 4 homes in this study. And obviously savings are very sensitive to the heating load as well as gas prices, and they're also sensitive to how we count them. So we have heating savings and heating and humidification savings combined. For these houses, heating only savings are between about 70 and 160 therms per year. And for heating and humidification, these are increased from about 170 to 290 therms per year. So these are really significant savings. What does that mean in terms of dollars? Well, it depends on the cost of gas. We have low, medium, and high prices. This is 50 cent, 80 cent, and 120 cent per therm. And the prices are what they are. Right now, we're currently at prices today that are represented on the medium scenario. So this is roughly, at today's gas prices, we're seeing $60 to $130 in savings per year on space heating only, and $130 to $230 a year on space heating with humidification. So again, this is only one side of the equation. This is how much we save. I mentioned earlier that we also documented how much it's going to cost. And so the headline here is that a TMH costs about $1,400 to $1,900 a year. Based on our experience and kind of a comparison on what entities say condensing furnaces installed should cost, we would say confidently that the TMH costs about 60% less than a condensing furnace installation. So that's a benchmark we can compare against. Installing a TMH basically has 3 components. We've got the retail price of the unit, which we say is between $600 and $940. This is based on work done by GTI and then modified by us for the difference in their reference design versus our TMH units. We do incur some materials cost in installation associated with the new venting, and in some cases a condensate pump to drain extra condensate coming out of the sealed vent. And then there's the installation labor, $460 to $660. And on the left, I have a chart that shows how this installation labor breaks out. So on the lower dark blue, we have the mechanical elements of the installation. This is doing the ducting and the venting, essentially, for the units. We have between about 5 and 7 hours. On top of that, we incur some costs to do the electrical work by wiring up the TMH and the fans. I will say that there was extra electrical and mechanical work in this project to facilitate our alternate mode testing. So that has to be taken into account, and that hopefully we could see slightly lower costs. On top of that, there are also some coordination, waiting around for different team members and or waiting for an inspector, and then finally some inspection work. You'll note on site H4, which is the first site we installed on, there's also this gray bar that took a long time. At that site, we had to replace some furnace return duct work. It probably wasn't necessary, but we wanted to make sure that this house wasn't going to behave oddly and essentially to make our results more broadly applicable, we wanted functioning return duct work. So in the end, you can see that these guys did a great job. They installed all these units in half a day. They tended to get better over time. By the end of the project, the last unit they installed in almost 8 hours among 3 people. I think they were in and out of there in under 3 hours. So hopefully in the future we could see these units installed by a crew at 2 or maybe even 3 per day for an installed cost of $1,400 to $1,900. So putting these pieces together, we can look at payback scenarios. So I'm going to be a little bit optimistic and say that we can install these units for $1,400 a year. And based on the savings, we get a variety of payback numbers. Before I go there, though, I want to draw your attention to the lifetime of a TMH unit. So a TMH is a really simple device. It's a heat exchanger. In fact, a heat exchanger that'll see less abuse than a regular furnace heat exchanger and inducer fan. And under nominal operating conditions, I think these things will work for decades. But that's really not an honest lifetime to consider for the TMH. We have to remember it is a retrofit device, and it's going to go on a standard efficiency furnace that previously exists. We'll make sure I get rid of that. So, in fairness, we think that we would like to install TMH units on standard efficiency furnaces that are between 0 and 8 years old, and this would put an upper limit on their lifetime of 12 to 15 years. So that's really, I think, the benchmark we should consider when we are considering cost effectiveness of the TMH technology. So that said, we calculated payback for a variety of situations. Again, our scenarios correspond to the savings situations we had at each of our houses and their weather normalized loads. And we calculated payback for low and high gas prices, assuming heating only savings, heating and humidification savings, and then heating and humidification savings under a variety of incentives. So there are several ways we could incent a TMH operation. So there's direct savings through space heating, so space heating conservation rebates. There's direct savings through high efficiency humidification, so humidification conservation rebates. The TMH effectively displaces the capital costs of another whole house humidifier, so there's also a credit we might apply there. And so some combination of those credits could be used to nominally come up with $200 to $400 incentives for end users, and we calculated paybacks under those scenarios as well. So the main point here is that aside from low gas prices and heating only savings, where we have pretty terrible paybacks of 17 to 40 years, almost all the other scenarios result in paybacks within the lifetime of the TMH unit. So even at low gas prices, heating and humidification savings or heating and humidification savings with some kind of nominal rebate, we get TMHs that we can install that will save more money than it costs to install them. If we look at high gas prices or consider where we are now, medium gas prices, we actually have, under some incentive scenarios, pretty lucrative payback periods on the order of 5 years or maybe 7 years at today's gas prices. But the big takeaway here is we're pretty confident under the vast majority of scenarios the TMH can pay for itself over its lifetime. I think the really important step. So where are we now? Well, I can give you some conclusions, and then I'm going to tell you what stands for the future of TMH technology. So for the houses and furnaces that we studied in this house, the TMH adds on average of about 10,500 BTU per hour to the output of standard efficiency furnaces. This is a direct natural gas savings of 9% for space heating, and then depending on the state of humidification in the house, it could be 9% additional savings and or simply a very nice non-energy benefit. Furthermore, it performs very similarly to a whole house humidifier that would be operated by a humidistat, but without the headaches of those systems. There's no controls, there's no maintenance, there's no plumbing for a water supply. It just operates passively, and its output, we've demonstrated the mechanisms, is just proportional to the need for humidity in a house. Consequently, in dry homes or mildly dry homes, we see indoor improvement in humidity of 10% in very cold weather. We see that humidity diminish in mild weather, and we also see that humidity output diminish in a home with naturally high humidity. As we just got done going over, the TMH is cost effective over its lifetime in most of the scenarios that we analyzed. In fact, it's the only real alternative for these cost-effective energy savings compared to a condensing furnace upgrade. And it does so at about 60% less installed cost. So when we think about this, it's really the only way we are going to achieve these high efficiency savings on this massive install base of standard efficiency furnaces that is going to slowly phase out over the next 20 to 50 years. But there's a caveat. I've withheld this the entire talk, and I'm now having to share this with you. So over the course of this project and in the development to it, GTI has tried to entice manufacturers to take up this TMH concept, and they've faced some stiff resistance. Two common reasons given to them by potential manufacturers. Firstly, furnace manufacturers are worried that TMH units could potentially cannibalize condensing furnace sales. This makes sense. It is an alternative to a condensing furnace. It happens to be a cheaper one, probably with a lower profit margin, and you can understand that businesses are not in the business of selling cheaper and less profitable products. Secondly, the manufacturers cite risks associated with creating a new product without an established market. So a furnace retrofit is not an established thing, and are risks associated with trying to convince people that it's a viable option compared to the status quo. And I think that currently manufacturers are viewing that as a risk that's not acceptable and doesn't justify a new development compared with, the regular way they go about making money. So this is a really unfortunate situation. What can we do? What can the CIP program do, or anybody interested in savings? Well, we've alluded to this earlier, but the TMH obviously saves energy. We are confident in saying that it's going to save about 9% savings for space heating, and it can save even more if you add humidification. So it is feasible that we can direct rebate these savings. That could be a way that we could convince manufacturers that there's less risk associated with these units. Maybe a more elaborate option is to actually develop a retrofit program in order to kickstart a market. In theory, we may be able to secure a sufficient number of participants up front that would justify a manufacturer going into TMH production and help them kind of alleviate this initial risk of kickstarting the market. Lastly, an option that we'll continue to pursue, and others may pursue too, is to pursue some kind of public-private partnership to lower the risks of commercialization. It's a common problem that businesses have to get from essentially the stage we are now to final commercialization, and there are programs out there to help companies do that. Some federal programs, namely Small Business Innovation Research and the Small Business Technology Transfer programs, have a history of getting past this problem. And so that's where we are now. I don't really want to end on that sad note, and so I have this plot again on the last screen to remind you kind of where we sit. So we've demonstrated this technology has an amazing promise, and really it's maybe the only viable way to get savings from our massive fleet of standard efficiency furnaces. And today we do have some hurdles to overcome. Namely, we've got to get somebody to build it. And when I started this project, I thought that this is something that has to happen really rapidly. We are transitioning to high efficiency furnaces, and if we don't get TMHs installed now, we're not going to get those savings. But this chart shows something quite different. We really took our time here in this model to look at all the scenarios. But any way you look at it, we're going to have hundreds of thousands of standard efficiency furnaces in the state for decades to come. So this means we have some time to overcome these hurdles. And I think that's a promising outlook, and I'm going to do our best to continue to pursue this technology and try to get after these savings that we otherwise have to let go. Thank you very much. Questions? My email and phone are up there. Our final report will be published soon, and I'm always available.
Thanks, Josh, for that great presentation, including your insights in the recommendations and looking forward. And now we're going to turn it over to Mark, who's been monitoring your questions as they come in. And Mark, do you have any questions for Josh?
Yes, got a couple of questions that came in for Josh and his team. First off, did you find any increased window condensation in TMH mode versus bypass mode?
No, we did not. I will mention that the high humidity house they have condensation events in very cold temperatures below 15 degrees. Below minus 15 degrees, and they didn't report any difference in condensation whether we were in TMH mode or bypass mode. I'll say they also had an issue with condensing on their cold water supply, but that issue was also present regardless of whichever mode they were operating in. So I think it's fair to say that in some cases it could be an issue with some additional condensation, but as we measured it here, we were either in dry homes that didn't have a problem or a humid home that had a problem regardless of what the TMH did.
Okay, thanks for that answer. The next question we have Do you think HVAC salesmen will be savvy enough to withhold selling these devices to high humidity homes?
That's a really good question. I think that we've put a little bit of thought into this, and based on the humidity monitoring we've done, it's actually quite easy. Basically, if you measure humidity in one of these homes during the wintertime, even a spot measurement, you can classify it into whether it's a high humidity or a low humidity home. So I think that we may need to do a little bit of convincing, but it's actually quite easy for us to determine whether a home will be a good candidate or not for a TMH installation. And right now I would put that at around 40%. If you can maintain 40% humidity in your home anytime between mid-December and mid-February, you are not a candidate for humidification. And if it's below that, I think you could take full advantage of TMH technology.
Okay, thank you. Those were the two questions we had come in, so I'm now going to turn it back over to Mary Sue to close this up.
Great. Thanks, Mark. The recording of this webinar and the final report both of them will be available on the Department's Applied Research and Development webpage, as well as on CEE's website. On the Department's webpage, when it's available, you can link to them from either the webinar quick link or the card search quick link. Could you move the next slide, please, so we can show that? Thanks. On this page, as you can see here, with the arrows there pointing to the two places that you can link. The R&D webpage has additional resources and information related to the CARD program and to the CARD research projects, which you can check out. The address for that is at the bottom of this page. So thanks again for participating. We appreciate your interest in the results of CARD projects. Before we leave, I want to take this opportunity to mention some upcoming CARD webinars. On December 19th, which is just next week, GDS Associates will report on the results of their evaluation of an innovative liquid cooling technology in a Minnesota data center. And on January 4th, Apprise Incorporated will discuss a study which sought to help the department and other Minnesota stakeholders develop a better understanding of how low-income conservation improvement programs in Minnesota operate and how we might make them more effective. Then in January, there are also two webinars that will be conducted by GTI, the Gas Technology Institute. And the first one is on the 25th, which will detail outcomes from the monitoring of a modulating gas valve retrofits and moisture sensor retrofits in commercial clothes dryers. And the second one on the 31st will report on their field assessment of an intelligent, networked, and retrofittable domestic hot water heater controller. Then in February, the Center for Energy and Environment will be back to conduct a webinar that summarizes the results of their evaluation of a demand-based circulation control for central domestic hot water heater systems with recirculation loops. Announcements about upcoming webinars and other news related to the Minnesota Conservation Improvement Program can be found in the CIP newsletter. You can use the link on this slide to sign up for the newsletter if you don't already have that sign up. In the meantime, please contact me if you want more information on these upcoming webinars or if you have questions, feedback, or suggestions for the CARD program or CARD webinars. Thanks again and have a great rest of your day.